Hello class, welcome to the forces video. Today you're going to learn more about forces than you probably ever wanted to know. We're going to go over a definition for force, we're going to talk about what net force is, we're going to talk about balanced and unbalanced forces, friction, air resistance, calculating force, and free body diagrams. You'll know you're successful if you complete your notes. Here are the notes. You have two options. You can either make a copy of this document and type out your notes and then print them and put them into your notebook, or you can just copy the table into your notebook and take the notes there. Either one will result in 100%, and doing anything other than that will result in a 0. Okay, so here we go. Oh, you'll be able to find a link to this document and a link to the presentation in the description of the video. Quick reminder, inertia. Love that GIF. Inertia is an object's tendency to do what it's already doing. An object at rest stays at rest. An object in motion stays in motion. The more mass an object has, the more inertia it has. In other words, the more it tends to do what it's already doing. Newton's first law of motion. So just got to remind you of that. Remember our GIF. Wait for it. Okay, yeah. See, like the books keep doing what they were already doing. They were moving, and then it hit the pivot. Okay, yeah, you get inertia. Anyways, let's move on to force. So there's two different definitions, which are really just one definition, but we're going to say it as two definitions right now. And the first one is that there's a force whenever there's a change in inertia. For example, we have here a box on a skateboard with a young child sitting on top of it. So if it is inertia, it's doing what it's already doing. In order to move it, I need to apply a force. Hey, I'm changing its inertia. I'm changing its inertia. Now I let it go and it just keeps doing what it already was doing, right? There's no force acting on it. Okay, so whenever there is a change in inertia. So let's say something's already moving, right? So it's already moving. It's going to need a force to stop it from moving. Oh my gosh, it's a man with the trash can on his head, with the girl on top of the trash can going 31 meters per second. It's not good. But if I apply a force, I can change their inertia to stop them from moving. This small wooden man is stopping them from moving, and eventually will change their inertia so much that they're no longer moving. Or almost. Okay, so there we go. Whenever there is a change in inertia, there is a force. The second definition, whenever there is acceleration, there is a force. So either positive or negative. Acceleration and force are very similar to each other. They're a very similar idea. Okay, so here's an example. We've got a box, and we've got acceleration, and we've got a person who can push this box, and I'm going to push it, and you'll see that when there is force, there is acceleration. Okay, check it out. Oh look, there's applied force. There's also acceleration. If there's no applied force, there's no acceleration. So it's very literal, this relationship between acceleration and force. If there is force, there is acceleration, right? And if I want to stop this, right, there's force, there's acceleration. That's an important idea, okay? Great. So there we go, the two definitions of forces. Our next thing that we need to talk about is this idea of net force, okay? So there's this idea that more than one force can act on an object, right, at a time. So it's actually happening to you right now. There are multiple forces acting on you, and you don't even know it. Forces are vectors. I think you might have noticed that there were some arrows in the last video, and if the vectors point in opposite directions, they cancel each other out, okay? The net force also called total force, or the sum of the forces, is the force that is left over after all of the vectors cancel each other out. Okay? So this is kind of easier shown than explained, so here we go. Here we've got two people things, green guy and red guy, and when I press go, they're gonna pull, and they're gonna pull, and you see nothing happens, right? You see that this is a vector, sum of forces and values, right? They're both pulling the same amount, and it's not moving anywhere, right? So there's zero net force. There's zero sum of forces, okay? But if they're unequal, then there is a net force, okay? So then there is a net force. So I'm going to get into that when I explain balanced and unbalanced forces. Balanced and unbalanced forces. So a balanced force, you can imagine when things are balanced, right, they're equal. And so if there's no net force, then the forces are balanced. If the forces are balanced, there is no acceleration or change in inertia. So that's what's happening here, right? The forces are balanced. Same on this side as there is on that side. The sum of the forces of the net force is 0. An unbalanced force, when the forces are unbalanced, there is a non-zero. I know it's kind of a weird word, non-zero, so not zero, anything but 0 net force. The force vectors do not cancel each other out, and there is acceleration and a change in inertia. So if I'm going to pause this, and I'm going to put another person here for Team Red, and you can see that now there is a net force, there is a total force, there's a sum of forces in this direction, and when I press go, right, the tug of war, red team wins. Okay, so if there is you can have multiple forces, and if they cancel each other out, then there is no net force. But if they do cancel each other, or if they don't cancel each other, then there is a balanced force. I know this is kind of confusing. We'll get some practice, just get down the notes and everything for right now. Okay, so friction and air resistance. So friction is something that we all know about and we've talked about, but I'm going to give you a good definition. So friction is a force that resists or goes against the direction of motion. It has to do with gravity and molecules. We'll be able to understand it better after Christmas, but here's an example. So check it out. We've got a refrigerator, and there's a small child sitting on top of it, because why not? And there's this person here, and they're gonna push against this machine. So they're pushing against this machine, but the machine's not moving because it has friction. And you see how I'm trying to make it push to the right, and the friction's going to the left. The friction of force is opposing the direction of motion, but I push harder, push harder, push harder, 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 and eventually there is a net force. And when there's there's a total sum of forces, right? The forces are unbalanced now, right? I'm applying more force than there is friction, and I'm going to begin to accelerate to the right, okay? So there we go. Now the friction is taking over. It's coming to a stop. And there we have it, all right? So air resistance is something else we'll talk about here. And air resistance is a specific kind of friction. It's a special kind of friction, and it's caused by air particles in our lovely atmosphere. And this is kind of a cool GIF that we'll look at again later, but this guy jumps out of the airplane. He's being pulled down by gravity. The air resistance equals the gravity, so he begins to travel. All right, and then he slows down when he deploys the parachute, and take a couple minutes, maybe look at this GIF. If it makes a lot of sense, great. If not, don't worry about it for right now. Okay, continuing. Calculating force. So, calculating force. Acceleration is really important here. So as you saw before, acceleration, if there's acceleration, there's force. If there is force, there's acceleration. So the way that we calculate force is really simple. We just take the mass of an object times its acceleration, and that gives us force. So for example, I push a 5 kilogram ball with an acceleration of 5 meters per second squared. What is the force? Well, all I do is I multiply 5 kilograms times 5 meters per second squared, right? Mass times acceleration, right? And I get 25 kilograms meters per second squared, or 25 newtons. So we call the unit for force is a newton, all right? And a newton is equal to 1 kilogram per meter squared. That's just how the units work out, okay? We have the lovely force triangle, which is great. You'll be able to use that to calculate mass from force and acceleration from force and mass. And this is Newton's second law. So there you go. And if we really think about it, force equals mass times acceleration. The bigger something is, the more inertia that there is, the more acceleration that you've got to have, well, okay. The bigger something is, the more force you need to make it accelerate. All right? So if you have a really large force and a really small mass, you're going to have a large acceleration. You have a really big mass and a really small force, it's going to be a really small acceleration. So check out this video. This is someone kind of fake kicking a bowling ball versus a balloon. So you notice that when it kicks the bowling ball doesn't go very fast. It doesn't accelerate much because it has such a large mass. It has a lot of inertia, right? Because it's so large. It wants to keep doing what it's already doing. Whereas the balloon is very light. It does not have very much inertia. So when he kicks it, it has a lot greater acceleration. Okay? So just think about that, trying to conceptualize the relationship between force, mass, and acceleration. Finally, free body diagrams. This is how we draw and represent forces interacting with objects. You represent an object, usually with the box, and you might put something like a name in there, like Jimmy the Pug, and then there's force vectors, right? You show the force vectors. So this would be like FA is like force applied, FF is force of friction, FG is like force of gravity, FN is the normal force, and we'll talk about that stuff later, but I just want you to know how to draw a free body diagram. Okay, so that was a lot. I know that was a lot. Good luck. Watch StudyCat for good luck. Meow. All right, do your homework.